Okay, if not, let's continue. I think we are into 20.3, and starting with the property of the function. I mean, property of Fourier transform. Um, I think we did the first one, but let's very quickly divide all this. So that's but the the thing to be careful, you need to be careful is the convention. Okay, this is the when you go back to your language or the notation or the textbook. The f of r now is r as a spatial variable, three-dimensional spatial variable. Take the Fourier transform, and now after take the Fourier transform, it's a function of the k vector of the wave vector, and this is defined as a g as a function of k, and it's given by the formula. This the symmetric convention. Put the f inside, and now this is I and k dot r. Okay, and so the convention is this, there's a positive sign in here, and you just need to follow the convention because many people will have negative sign. So that will change your formula. So you remember, just memorize the formula and not pay attention to convention. Sometimes you might make a sign error somewhere. Okay, so that need to be a little careful. Now the first one we already did that. So r minus a capital constant vector r. Just by the definition, just put f capital R here. Okay, copy everything else. And the trick is now we define your variable, so call this alpine. Call this alpine. Right. And the idea is that alpine is just shifting r by a constant vector r, so the volume element doesn't change. Okay. Let's say fix this. Well, you need to make the corresponding change. So r prime equals r minus r, so r equals r prime plus r. And then you have an extra term that's outside of the integral. Right? And you recognize that this is just your original g sub k. Okay, this is g sub k. No, g as a function. G as a function. Okay, so that's the first property. It's okay. So we'll repeat that just remind you that how it's doing, so that you see that it's straightforward. So I mean, it doesn't have you don't need to actually memorize all these formulas. Just remember the process how you get the result. Okay, and then we can keep doing that. Is that okay? The first one. Okay, now we go to the second one. Your question? Someone asked a question? No? You're missing something? I erase it. Okay. I mean, I'm recording it, so if you miss anything, you go back to the class video to look for that. If you miss. And then the next one is alpha, just a constant alpha terms. Oh, I think in the text we implicitly assume alpha is positive, which is not necessary, but we can work out the genuine case of either sign of alpha. So just by the definition, put alpha r in here. Okay. And so using the same trick, we define this as our point. Okay, and obviously you need to change the volume argument because you multiply by something, and so the the dq alpine, because r is alpine is alpha times r, so so this will have alpha cube, but then one elements is by definition positive, so this is absolute value or absolute value, the cubic power. If alpha is negative, okay. So, if you do that, substitute back everything. This is you divide alpha to and then you add alpine, and then into the I A, and R is alpine divided by alpha. You divided by alpha. You put the alpha in the K, and now this is your new K. So K over alpha is a new K. DQ alpine. Right? You compare this form to this one, and you realize this is G of K divided by alpha. Okay, yeah. Alpine is the integration variable. So compare this form with this form. Yeah. So this will be like a K in here. And this K go into the argument of your function G. So this will go into the argument of function G. So K over alpine, this is alpine, because alpine is alpha times R. So R is alpine divided by alpha. R is alpine divided by alpha. So K, so you put the alpha in the K, so K divided by alpha is the argument in here, so you go into the argument of G. Okay, so that's how you get the second equation, 20.49. It's okay. So again, the textbook doesn't have the absolute value sign because it's assumed it's positive, but if it's negative, then obviously it's you have the absolute value. So that will bring the third case much easier because now you change it to negative sign, just minus R. Obviously, everything the same except you choose alpha equals to -1. So for this case, alpha is -1 doesn't change the absolute value. So for this case, obviously, compared with this one, it's just G of minus Q. Right? Only change is over the argument of G. Right? It's okay. So by consider alpha that can have sign, you cover the third case also. It's okay. So, and now the fourth case, 20.15. Now instead of just this one, not getting too complicated. So let's start over. Okay. Now this is taking a complex conjugate and also change the argument. So change the argument and take the complex conjugate, right? And so okay, so you do it the same thing, same way, except that now you because you have a complex conjugate, you want to get rid of that by taking a complex conjugate of the whole thing. Just put the F in here. And whatever in here, you need to change it to minus IP that all. And take the complex, put the complex conjugate out because everything else are real. Right? We take the complex conjugate, only change the complex conjugate and change I to minus I, go back to here. Okay, and now you do the same trick as this one. Change it to alpine, and doesn't change. So let's just if I do the erasing trick, that may be too confusing. Alpine, right? Alpine that becomes negative, so you have a negative sign. Alpine. And DQR is the same as DQ alpine because this volume element doesn't change. It's defined positive and compact conjugate. Okay, now you recognize this is exactly this way. This complete. Okay, is that right? So this is basically two cases. One is taking complex conjugate, the other is taking the negative sign of reversing your variable, direction of your variable vector. You don't have to combine them. You can just do one at a time. You change this to positive, then you change the sign. Yeah.
Why should one of the axes be positive?
Which is one?
You said the modulus of alpha came because one of the axes is positive.
No, the volume element is positive, defined as positive. So volume element is dx, d1, dz. Whatever the limit, this is all into, right? If you change the negative sign, everything changes the negative sign. Or individually, it doesn't matter. Change individually. But then if you change the negative sign, then you also need to change the limit because we redefine it. Then you can use the negative sign to shift the limit back to the original one. So it doesn't change. So the volume element is always part. You can say it's a volume. So we define your variable. You basically reflecting all your spatial vector. The volume is still a volume. It's a positive definite number. Okay. Now the next one is slightly complicated. Yeah. Is it okay up to here? You copy anything? All right. The next one is the gradient. Let me put a gradient inside. Gradient. Okay. And now we put a gradient up left here. Okay, this is operators on just an F. Okay. Okay, so what you can do is do a integration by parts, right? So you have a gradient of the whole thing, gradient of that, all, right? And now you need to subtract something because gradient of this one give you this one because you operate on the first vector and keep the second vector as a constant vector. And then the second term will be take the gradient of the exponential function. So you need to subtract that part. You subtract f gradient of okay. Now the assumption is that f is falling off fast enough at infinity. That's mean f is well behaved. Otherwise, the Fourier transform may not be definable or may not be well defined. Although there could be exceptions when we define Fourier transform of delta function also, or constant value, that might be tricky. But excluding those cases, the gradient of the whole thing and integrate over the volume will give you only the boundary terms. And the boundary value of f tends to 0, so you can say you just forget about the total derivative terms. Okay, we keep just the second term. Now the gradient of exponential function, how do you know how to do it? You all know how to do it, the gradient. Is it true for everyone? You just go back to your definition. Right? So gradient is just x positive positive 1. And e to the ik, it's k dot r is just going to I x plus ky y. Yeah, and you operate this to that. The x component operate only the first argument. We'll give it pull our I k sub x and then multiply by the unit vector kx. That's the first term, and then plus the second term, which is I k sub y times y unit vector, and then the third term plus I k sub z times z vector, and multiply by the original function. So gradient of this is equals to just pull out everything into the I k, copy the function back. Is that okay? The boundary term has it's a gradient just like this one, right? So you have total derivative acting on the whole thing will give you the boundary like at x equals to minus infinity and infinity, right? And you assume that f fall off fast enough at infinity, so at all the infinite terms at f at infinity will be 0, so you can ignore that, right? Just and then y term is the same, z term is the same, so all the boundary term will be 0. No, the boundary term you assume this is basically assuming that f is infinity. This is c. That's the implicit assumption. It actually is, you could write a little bit more rigorous. It falls fast enough because the volume element also increased. So you need to. But this term doesn't matter. This is just a sinusoidal. No, after you take the integration, you give it the boundary term, right? So let's just write it here. Let's consider the first term, the gradient, the partial x integrate whatever L, right? And you have a dx. The volume element has a dx, right? This is minus infinity. This is the total derivative. Did that give you F? That wrong. Value at minus infinity. And you assume F fall off fast enough, and that will be 0, right? At both end of x, that will give you F is 0. Okay, so that's the argument, right? But this is after you do the integration, this will be a boundary term because right, it's evaluate at x is minus infinity and x is infinity. This one is not a boundary term. The first term is a boundary term. This one is not a total derivative. This one you use this one. This one. This one you don't do an integration. You use this one. We work out this one. Work out the gradient of the exponential factor, which is given by this one. You still need to do integration. That's the next step I will write down. This is a volume. This is still a volume integration. This is still a volume term, right? We haven't done the integration yet, right? This one we do the integration and argue that this term will be 0. Okay. Now you substitute this back to here. You get the and you have a minus sign, the minus k, and you multiply the f and f o, and then you have e to the n k o, theta o, theta o. And this I minus ik vector actually is independent of integration. You can take it out, and the rest is just the same. Okay, so you can just write minus ik and g. Okay, okay. Okay, so that's 20.52. It's okay. So that's how you get it. And the last term is the same. Now once you do that, the other is just it's the Laplacian. Laplacian is the divergence of gradients. So basically, now you take another divergence of that, and now you do the same trick and do the same integration by part, and basically that will pull out another factor. Instead of going through everything, that one would be I minus ik dot into minus ik and g, which is minus k squared. Okay, and that is the Laplacian. Okay, I skipped the integration by parts first because it's exactly the same. So these are 3D, and they are corresponding equation in 1D. I think there will be a homework problem asked you to write down the 1D property just like this. It's straightforward. It's doesn't matter. And in 1D will be like 20.52 to define. Instead of a gradient, you can consider just a derivative, and also n derivative, just like this is second derivative. If you have n derivative, you just multiply by instead of 2 square, you get the n factor. So that's 20.55 and 56. It's just like the same, except in 1D, your text would like to use omega instead of k. It doesn't matter, right? Instead of x equal t, it's the same. It's okay. So that's all those properties.